In a modern distributed application, web, mobile, and IoT clients are simultaneously connecting to dozens of different microservices across a fractured internal infrastructure. When developers first build these systems, they often allow external clients to route requests directly to those individual internal services. The mobile app queries the user service, then queries the billing service, then queries the inventory service. This creates severe architectural drag. First, it forces massive code duplication. Every single one of those 50 internal microservices must independently implement, execute, and maintain its own authentication logic to verify who is making the request. Second, it fractures the attack surface. With external devices speaking directly to internal servers, every microservice must be exposed to the public internet, multiplying the entry points for potential exploitation. Finally, it relies on highly complex client-side routing. The application running on a user's phone must somehow map and resolve dynamic, frequently changing internal IP addresses over an unreliable mobile network. Routing external traffic directly into an internal cluster degrades network performance and drastically increases security overhead. The internal topology requires an architectural abstraction. This illustrates the API gateway, a highly available reverse proxy deployed at the edge of the network infrastructure. External clients now see a single, stable interface. They send all requests to the gateway, completely blind to the complex cluster of microservices behind it. The gateway's primary directive is centralizing cross-cutting concerns. Instead of 50 microservices handling their own security, the gateway intercepts every inbound request to enforce routing, authentication, and rate limiting in one place. Introducing this abstraction requires an engineering compromise. By adding a new network hop between the client and the backend, the gateway injects a baseline latency penalty into every single HTTP request. This latency penalty is a mathematical necessity. The few milliseconds lost at the edge are heavily outweighed by the processing time and bandwidth saved across the backend cluster, which no longer wastes CPU cycles rejecting unauthorized traffic. The API gateway represents a deliberate architectural trade-off. It shifts infrastructure complexity away from developers, concentrating the heavy lifting into a specialized, high-performance edge node. At runtime, the gateway functions primarily as a centralized, high-speed routing table. It inspects incoming HTTP request envelopes to determine exactly where the data belongs. The most common method is path-based routing. The gateway reads the URI prefix, for example, mapping any request starting with /users to the user microservice cluster and /payments to the billing cluster. It also executes content-based routing. By evaluating HTTP headers and payload metadata, the gateway can route traffic to specific API versions or distribute subsets of traffic to a staging environment for a canary deployment. Once the destination is identified, the gateway often has to modify how the data travels through protocol translation. Public clients typically communicate using standard HTTP and REST APIs, but internal microservices are designed for speed, relying on highly efficient binary protocols like I. Protocol translation decouples external interface constraints from internal demands. Clients get the standard web protocols they expect, and the backend gets the high-performance binary formats it requires. Beyond routing, the edge gateway serves as a centralized validation checkpoint. It must authenticate every request to shield the internal network from broken authentication attacks. Traditional API keys present a performance bottleneck. Validating a static key requires the gateway to execute a database lookup on every single request, introducing severe I/O latency at high traffic volumes. Stateful protocols like OAuth 2.0 introspection carry a similar penalty. The gateway must execute an external HTTP round trip to an identity provider to confirm if an opaque token is still valid. This diagram illustrates the optimal low-latency solution, stateless JSON web tokens. The payload carries a cryptographic signature, expiration timestamp, and permission scopes. The gateway verifies the signature locally against a public key, establishing trust, then parses the expiration claim to ensure it remains active. Finally, it validates the scope claim. Even with a valid signature and an active timestamp, the gateway confirms the client actually possesses the precise authorization required for the requested route. By utilizing stateless tokens, the gateway shifts authentication from an I/O-bound database problem to a CPU-bound math problem. This reduces validation time down to microseconds. The final defensive responsibility of the gateway is rate limiting, restricting the volume of incoming traffic to protect backend services from denial of service attacks and cascading resource exhaustion. In a distributed system, running rate limiters in local gateway memory fails. If a client hits different gateway instances behind a round-robin load balancer, their request count is split, allowing them to easily bypass the intended limits. To enforce limits consistently, the architecture requires a centralized high-performance in-memory data store, typically Redis, to maintain global rate-limiting state across all gateway nodes. The simplest approach is the fixed window counter. It uses standard Redis increment and expire commands to count requests within a static timeframe, offering extreme memory efficiency. This graph illustrates the fixed window's fatal flaw, the boundary burst. If the limit is 10 requests per minute, a client sends 10 at second 59 and 10 at 61. The backend is slammed with double the allowed traffic in just 2 seconds. To fix this, engineers use the sliding window log. This algorithm utilizes Redis sorted sets to record the precise timestamp of every single request, completely eliminating boundary bursts. However, the sliding window log carries a heavy memory overhead. Because it logs exact timestamps, the required storage scales linearly with request volume, threatening to exhaust Redis capacity. The industry's standard compromise is the sliding window counter. In this updated graph, the sharp traffic spike is algorithmically flattened into a smooth, distributed curve. The sliding window counter merges the memory efficiency of a fixed window with a weighted rolling average, smoothing out boundary bursts without requiring a massive memory footprint. Alternative algorithms fit highly specific use cases. The token bucket algorithm intentionally allows controlled bursts for batch processing, while the leaky bucket algorithm strictly shapes irregular inbound traffic into a flat, steady outbound stream. Selecting a rate-limiting algorithm is a strict mathematical compromise. Systems architects must balance memory overhead, boundary accuracy, and acceptable burst behavior based on their specific backend capacity. We can now trace the complete path of a single HTTP request hitting the edge of the data center. This schematic details the sequential checkpoints. The request enters the gateway and hits the Redis rate limit check. It passes. The JWT cryptographic signature is validated. It passes. Finally, the route table lookup executes, translating the protocol and forwarding the data downstream. This entire complex validation pipeline executes in single-digit milliseconds. The client perceives the response as instantaneous. The API gateway relies on a clear architectural calculus. By accepting a slight controlled latency penalty at the network edge, the system achieves massive security and compute efficiencies in the backend. Centralizing these cross-cutting concerns into a high-performance perimeter frees engineering teams from building redundant security checks. They can iterate on backend microservices independently, ensuring the reliability and scalability of the distributed system.